let's do an example problem that involves lots of forces acting on a single object, and that object accelerates. So it's no longer in equilibrium. There's actually some unbalanced forces. So what I have here is an airplane, a 6,000 kilogram airplane, and it's flying along at a nice horizontal steady pace, except it is getting faster. It's getting faster at 3.6 meters per second. So let's label the forces that act on it. Force due to gravity pulls down. Over here it says the wings provide 50,000 newtons of lift. That means the wings themselves are actually helping to keep the plane up. The engines don't have to do it, so this is 50,000 newtons. Now, the plane is actually accelerating forward or to the right at 3.6 meters per second, and so I'm actually establishing my frame of reference when I say that. I want the positive x direction to be the direction of acceleration, so I'm going to establish this like that. Y is, of course, perpendicular to x. Now, what I want to find is find the force the engine exerts. Well, that's a little misleading. The force the engine exerts is going to be down in this way, right? The engine exerts the force that way. The air, on the other hand, which actually makes the plane go forward, is exerting an equal and opposite force backing up. So if I can find this force, Newton's third law will give me that force. So let's take a look at all these forces. First, this force, I'm going to call it just F, has components. Since I picked x and y to be horizontal and vertical, I want the components of this force. So here's the x component, so I'm just going to call it Fx, and the y component of that force, I'll call that Fy, is right there. Now, we go to Newton's second law and we try to solve this in both directions and see what we get. So what I get is the net force in x. Now let me come over to my picture and look. Well, Newton's second law says this is mass times acceleration, right? The only force I have that acts in x is Fx. So I have Fx equals mass, which is 6,000 kilograms, times its acceleration, which is 3.6 meters per second. So I already know the net force in the x direction. So if I take 6,000 times 3.6, that's 21,600 newtons. 21,600 newtons of force are acting just in the x direction to keep that plane flying forward and accelerating like that. Now if I switch to the y direction, the net force in y is, let's see, now I've got lots of forces in y. I've got this 50,000 newtons of lift, minus this force due to gravity, its weight pulling it down, plus this force in the y direction, whatever it is, Fy, equals ma, Newton's second law, except that it was flying horizontally, so it's not getting higher or lower, it's not accelerating up and down, so that's 0. So the acceleration in y is 0, even though the acceleration in x is not. So I'm going to redraw this, 50,000 minus Fg. Well, Fg is the mass of the plane, 6,000, times the acceleration due to gravity, 9.8. Now you'll notice I already took care of the negative by subtracting it instead of adding it. Don't make it negative twice. Plus the force in the y direction, Fy, equals 0. Well, this is 50,000 minus 6,000 times 9.8 is 58,800, plus Fy is equal to 0. So I can add these together, so I have negative 8,800 plus Fy equals 0. So I end up with Fy equals 8,800 newtons. Now, neither one of those are my answer, right? I've got to put those together to get my answer. So I see that I have, that was like the horizontal line, I have my x direction, 21,600 newtons here, shouldn't be there, and I've got 8,800 newtons here, and my net force, or the force and this isn't the net force, this is the force the air exerts to keep the plane moving forward. Let's see, 8,800 squared plus 21,600 squared raised to the 1/2 power, 23,323.81 newtons. Okay. That's how much force this thing is pushing with, that's how much force the air is pushing with forward on the plane. Now, remember, a force is a vector, so I actually should find that angle too. So I want the angle, that's the angle whose tangent is 8,800 over 21,600. So if I do that math, 8,800 divided by 21,600, second tangent of that, 22.16 degrees. So this equals 22.16 degrees. So the force the air exerts on my airplane is actually equal to 23,323 newtons at 22.16 degrees above horizontal. Now if I wanted the force the engine's exerting, remember that force of the engines is equal and opposite to that, so it would be 23,323 newtons. And I could actually just say this, negative that at 22.16 degrees. If you wanted to add 180 to that and say at 202.16 degrees, you could do that too. Okay. Now, this is interesting because I found the force of the engine on the plane. I didn't find the net force. If I want the net force on the plane, that's pretty easy. That's just its mass times its acceleration. The only unbalanced force on this whole thing is this Fx. So that Fx is the net force. So the net force acting on the plane is 21,600 newtons. But in order to actually get this plane to do what it's doing, the engines also have to provide some force to keep it in the air. So that 23,323 newtons is the force the engines have to exert. So that's how we deal with problems with multiple dimensions, lots of forces. Just keep track of all your forces in all your directions, keep track of your accelerations, and you can find your forces in each direction.